Well, I don't know about you all, but the Ohio Valley finally got to me. I'm experiencing allergies for the first time this year. And Bill, I appreciated your presentation, and Dr. Holcomb, that makes me want to fog my bedroom and eat off the ground. Maybe it'll help me. Our next presenter is going to present about racing surfaces and testing laboratory. Dr. Mick Peterson is the Executive Director of Racing Surfaces and Testing Laboratory and also a mechanical engineering professor at the University of Maine. Please welcome Dr. Mick Peterson.
Hello, it's always a pleasure to be in front of this group. Thanks so much. I want to note that I've got some co-authors on this as well that have helped out. I'm going to talk a little bit about the data. One of the things that we're focusing on in this Welfare and Safety Summit from the very beginning was developing a culture of data in the racing industry. The Equine Injury Database is the most important aspect of that. This is the longest standing and probably most significant effort that's been made. More recently, the Jockey Injury Database has begun to develop the same sort of information for the riders that we've had for the horses. What my focus has been on is what I refer to as the maintenance quality system, which is taking and developing data associated with the design and the maintenance and the track inspections that are done prior to the race meets at the participating racetracks that you can see. We've at this point, the data is in its early stages and still developing, but it's important as we go through this to begin to tie the pieces together and to use them for action to protect the health and safety of the horses. So what is our goal? We could talk about performance, and certainly in the other equestrian sports, a lot of the focus has been on the performance of the surface. But really, the take-home message of the Welfare and Safety Summit has been from the very beginning is tying this to the epidemiology for the health and safety of both the horses and the riders. So what I'm going to talk about today is a useful result, a preliminary result, but a useful result. So at this point, we have for about 40 racetracks, we have basic track design information, turn radius, banking, the different types of designs that are used in the dirt racetracks in the United States, as well as obviously the different types of surfaces. Tying this back, though, to the Equine Injury Database is when we begin to get some sort of an actionable result. It's when I'm asked at a racetrack, is it a good surface? The question is, it's a good surface if it's a safe surface for the riders and horses. So what I'm going to talk about today is looking at the turns. This is one of those things that's been an ongoing question for the riders, owners, and even the fans, where they talk about banking, turn radius, a lot of the details of the design of the racetrack. So, how do horses turn? Okay, there's a centripetal force. We know Newton's first law. If an object is in motion, it's going to remain in motion. It's going to keep going in a straight line unless you act on it with another force. Turning requires a centripetal acceleration. The force that will turn it is another force that will actually allow the object to turn a corner. Otherwise, it'll just keep going in a straight line. The resulting force for the horse turning the corner is a ground reaction force. In order for the horse to rotate through the turn, there has to be a force that's applied from the surface, that's applied from the surface by the hooves, that's turning the horse in the turn, boy. So it's related to the velocity squared, which means that a small change in speed has a big change in the force, and it's also related to the radius of the turn. So the forces are significant. Let's take an example. A 415-foot radius turn, the horse is going 40 miles an hour, you get about a quarter of the acceleration due to gravity. So you think about the force that's associated with the weight of the horse, or the acceleration that's related to the weight of the horse, you've got about a quarter of that even in a 415-foot radius turn. So that's about 250 pounds of force for a 1,000-pound horse that's providing lateral forces that are the turning force. So if you think about this, you've got the horse, two legs, legs are not very far apart. There's a tipping force on the horse. That has to be resisted on the ground. There's going to be an outside force and an inside force that's going to be actually turning that horse to keep it from tipping over, because the horse wants to be upright. Okay, so we've got the weight of the horse also continues to apply. So you think about that. You've got a tipping force as well as a weight of the horse pushing it down. So you've got 1,000 pounds down, 250 pounds trying to tip it over. You add those together and you get some sort of a combined loading that's kind of pushing this over but still holding the horse downward. It makes perfect sense that there'd be some laterality of injuries. There'd be one side that would break and the other side that would be have less loading because of this tipping moment. But what this suggests is that it'd be the right leg that would fracture. If you think about it, if the horse is trying to tip to the outside of the turn, you would expect it to be the right leg that fractures. No. That's not the classic fracture that you see in a horse. So when people try to think simply about turning in a horse, they're probably wrong. It's not simple. Because the horse, this doesn't match the data, the simple analysis doesn't match the data. So what else resists the tipping? There's a lot of discussion of banking. Banking in the track can keep the forces moving between the two legs. That's good, right? We want the force between the two legs, so we're balancing the loading on the two legs. That resists the tipping, so we do that. Keep in mind we have 1,000 pounds pushing down, 250 pounds pushing to the side. Well, to completely resist that, we need 25-degree banking. Think about that on a dirt racetrack. Obviously not practical. We're not going to do that, okay? So there must be something else happening. Well, it's a horse. It's not this rigid thing that I have shown on the right side of the screen, or the left side of the screen there. It's a horse. The horse leans. They lean a lot. And this is a video. You can't see it. It's not running. But it gives you an idea. Okay, so as the horse is turning, they're going to be so how much do the horses lean? Well, we don't have a lot of data from a gallop. We've got more data from other gaits. Okay, so what can we measure? We've got kinematics. That tells the position of the horse. It tells the position of the limbs, the position of the horse, the leaning, the rotation of the hooves, and the relative position of the hooves. Kinetics, then, are the loads on the two hooves, the way the horse is shifting the load between the two legs. If we had a perfect banking and perfect leaning, we could distribute the load evenly between the two legs. The obvious outcome of this would be some sort of different laterality of injuries. And so this may be the insight that we need, that not all the fractures are on the right-hand side like we thought. Okay, so what do we have for measurement techniques? The kinematics typically is done with 3D optical, so they're markers, and this is an experiment that was done in Scotland on a banked lunging ring. And now more recently, there's work that's been done with inertial sensors. So the sensors can be placed on the horse, and you can get these positions without having to do this with all the optical cameras and setup. We also need to know the forces, or interested in the forces. This was traditionally done with force platforms, but that, again, somewhat limits what you can do. But more recently, there's been a lot more work that's been done with force measuring horseshoes. And that's Sue Stover's group and the group in France have both done this. Okay, so what do we get out of this? Well, I'm going to limit myself to discussing trotting because we've probably got more data on trotting. But if you think about with the data that we've gotten out of these two studies from France and England is that the inside forelimb is more inclined towards the body. The outside forelimb is less inclined to the body. So what you're seeing the horses positioning the cannon bones on the left and right to orient the horse to support that center of mass to project that load down into the surface. So these are even at trotting. These are relatively low speeds. So these angle of these limbs are significant even when we're talking relatively low speeds. There's not a lot happening on the hind limbs, but in the forelimbs we're seeing significant motion. If we look at the head and trunk, though, the center of pressure moves 3/4 of an inch to the inside of the circle. Again, this is just on trotting, relatively low speed, 3/4 of the inch. So the horse is leaned enough that's moving their entire center of mass of the horse 3/4 of an inch to the inside. Also moving the head and the head nod, using the mass of the head trotting to the inside to balance the gait and to balance the whole thing out. So even at low speeds, we have significant lean. But there's a problem with everything I've been talking about. I'm assuming a spherical horse. That's the punchline to a joke for physics people. So we've assumed that this is a spherical horse. It's obviously a lot more complicated. We've got the entire body of the horse that's moving. All right, so the body of the horse is moving around the turn, and the horse itself has to rotate. There's a trick we can use. We can actually take a motion of a point, and then we can add to it the rotation of the horse separately. Looking at the two pieces separately, then we can figure out what's rotating the horse. Pulling with the left front and pushing with the right rear, you can picture this horse then rotating itself. We're separating out these two effects that we have. We've got the effect of turning the corner, then we've got the effect of rotating the horse. We've separated out the two of them. This begins to give us the insight into what's happening with the horse that leads to these fracture patterns that are much more familiar to people who know more about horses. So what's happening to those hooves that allow this horse to rotate? The inside forelimb has abduction, it's away from the midline, and internal rotation moment at the hooves. So those hooves are actually rotating around and moving towards the center of the hoof, towards the center line or away from the center line in order to rotate the horse around the turn. The center of pressure on the hooves themselves then moves either towards or away from the midline. So what this center of pressure is moving is it's actually forming banking within the surface itself. So what's happening here? The hooves are actually rotating around, they're moving the horse around the turn, and then it's twisting underneath in order to create its own banking. Sounds to me like this may have some significant effect on surfaces, because how can you get a hold of that, and how can you rotate the hoof down into it if it isn't affected by surfaces? So, turns and makes the banking, and the surface then has to support the hoof. Okay. So now the obvious outcome looks a lot more familiar. Fractures left front and right rear because we have this rotation. Those are the two limbs that are turning the horse around, separate from the banking piece, just the turning the spherical horse. And then we have lateral loading to the outside. So we have the left front and right rear fractures, which would be much more familiar. Okay, so what do we see then when we look at the equine injury database? So we've talked about the physics of it, and then it turns out that no, the left front and right fracture differences are primarily on dirt. So we still see some effects between the laterality of injuries, some limited effects in synthetic and turf, but those left front is only significant relative to the dirt and the synthetic, relative dirt and synthetic and turf and synthetic. So we're seeing the laterality of injuries is associated with the type of surface. Why? Okay, so the horses align themselves to go around the turn. They've reduced this tipping moment, they created the banking. So what we've done is we're using the grip of the surface is affecting the ability of the horse to move the center of mass far enough inward. So there's been some work done on this. Now this was done in the UK. It was with polo ponies and race horses, but it was all done on grass. Well, they had sufficient grip that what they could do is they could look at the two factors that might limit the turning performance: peak limb force and traction. The horses would slow for the turn, regardless of what the factors were. But depending on the speed of the horse, at lower speed, it was associated with traction. At higher speed, it was associated with the ability of the horse to produce enough force to both turn as well as propel themselves forward. So you see the two segments of the curve there. You see in the first segment of the curve, it's traction limited. In the second segment of the curve, it's force limited. So what about racing? Well, what's probably happening here is that we're looking at synthetic and turf, which are force limited, so the horse is able to move the center of mass sufficiently that their full propulsive force is able to turn the corner. In dirt, it's probably the other effect that's traction limited because they're not able to orient themselves and have sufficient footing in order to turn. Okay, if traction limited, the ability to balance load between the limbs is limited, then turning then becomes an exposure variable for the horse. It's possible that traction-limited surfaces create a limited number of allowable turning strides for the horse. Because of the uneven loading between the limbs, because there's not a sufficient ability to rotate the center of mass inward, at that point the horse is limited. It's probably saying that a lot of the work that was done with Dr. Stover and her research group, where we talked about the number of fast works that the horse can do, we may be looking at a similar effect here where there may be a limited number of turns that that horse will be capable of doing. So the real question for us is what's actionable? What can we do as an industry or as to guide or to understand what's happening to eliminate the laterality of injuries? And it may be that this may be a significant factor, this laterality may be a significant factor in the difference between the injury statistics on turf and synthetics versus dirt. So we need to understand surfaces and turning. Is turning a factor in safety on turf and synthetic? What factors can be modified with dirt to provide this same ability to reduce the laterality of injuries? Obviously, it's not 25% banking, that's not practical, but there's got to be practical things that be done. It all gets back to understanding the musculoskeletal disease associated with these risk factors. We know there's a difference between turf, dirt, and synthetic, and Dr. Parkin will be talking about that after I'm done here. But our goal has to be to make dirt consistently safe. What we see on dirt is we see good years on dirt are quite safe. What we also see on synthetic surfaces is that every year is a pretty good year on synthetic. We see much less variability from year to year. So the goal should be to eliminate the bad years on dirt. And this suggests that turning may be a factor. And what I've always said, those of you who have listened to me before, water is obviously a factor as well. Okay, so what is the maintenance quality system? The idea is to take the type of dirt tracks, shallow sand, cushion, false base, look at turn radius, looking at banking and transitions. These are the sorts of design data that vary between racetracks that haven't been consistently understood and haven't even consistently been measured. Track inspection data allows us to understand the grip, the firmness and cushioning, and the consistency of the surfaces. And then finally, the maintenance data. When is the track sealed? Weather, drier than normal conditions, wetter than normal conditions. And then understand that there's a lot of differences in the horses that are running on the different surfaces. We have to control for the type of horses, the training, and the jurisdictional issues. And the idea overall has to be to reduce the risk to the equine athletes and their riders. So the overall theme here is a culture of data. The equine injury database, the jockey injury database, and the maintenance quality system. As we begin to tie these together, we can tie together the factors that associate risk and the safety in order to provide safer racing surfaces, safer racing conditions, safer racing design in order to use this data effectively. Thank you very much. Kathy, question?
Yeah. Excuse me, we do have a question for you. How does the weight balance of the rider affect the physics of how the horse turns and thus affect potential injuries?
Well, that's an excellent question, because what you see is the riders are usually acey-deucey, or whatever the right term is, towards the inside of the turn. And so we've already got an imbalance on the loading. But as you think about the turn, what that's doing is it moves the center of mass between the forces between the two legs. So during the turn, that's a factor that again helps create the balance between the two legs. In the straights, obviously it has the other effect. So that's one more factor. So not only is it lean of the horse, position of the limbs, position of the body, but then it's position of the rider as well. Any other questions? All right. Thank you very much. Yeah, you do. You do.
So Dr. Peterson has left me with the task of explaining AC-DC and why jockeys do that, because now people are going to want to know, why do jockeys do that if it's going to offset the balance of a horse? So I'm going to have to step out here. Actually, I'll use this microphone. So when I learned to ride, I just was taught to have my irons offset like this. And the reason why we have the one on the left side longer than the one on the right side is because they lean into the turn. The other advantage of doing that is if you think about somebody's going to walk up and push you, and they're going to give you a chance to find your position that you want to be in before they push you. Are you going to want to stand like this, or are you maybe going to want to stand stagger stepped a little bit? And so that's the other advantage of a jockey riding AC-DC, is that it really helps our balance and helps, especially if a horse stumbles out of the starting gate, where you can have a foot behind you and a foot forward and not fall off the horse in the very first jump.